Welcome back to the Deep Dive. Our mission today is, well, it's pretty profound when you think about it. We're pulling back the curtain on the very architecture of our digital world.
And when you look closely, you find one person's work is just, it's absolutely everywhere.
Exactly. We're talking about an American computer scientist who is, and I don't think this is an exaggeration, quite possibly the most influential technologist you've never heard of. He's just completely under the radar for most people.
It's astonishing, really, how central his role was. The code he wrote, the concepts he developed, they're essential to literally every device you use.
The phone in your pocket.
The phone in your pocket, the network that's delivering this audio to you right now, the servers hosting the files, the operating systems that run Wall Street, it all goes back to him. His name is Dennis Ritchie. He lived from 1941 to 2011.
So the big question we're trying to tackle in this deep dive is to really understand the mechanics of that influence. How did one relatively quiet researcher working almost his entire career at Bell Labs co-create the Unix operating system and, maybe even more importantly, single-handedly engineer the C programming language?
And those two things together, Unix and C, they really do form the absolute essential DNA of the entire modern digital age. It's not a stretch to say that.
It really isn't. So to unpack all this, we've pulled together a lot of material. We've got a comprehensive biographical study on his career, some internal histories from Bell Labs, academic papers that break down the architecture of C and Unix, and the official citations from the major awards he received.
Right. And our goal here is to get past just the facts, the dates and names, and really understand the conceptual breakthroughs that made his work, well, immortal.
Okay, let's do it. Let's start right at the foundation. Dennis Ritchie, born September 9, 1941, in Bronxville, New York. His professional destiny, it seems, was almost predetermined.
It really was. You could almost call it a generational mandate, and that's a key detail that, sometimes gets lost when we talk about this myth of the solitary genius.
But never that simple, is it?
Never. His father, Alistair E. Ritchie, was a longtime Bell Labs scientist himself, a real expert in switching circuit theory. He even co-authored a pretty significant textbook, The Design of Switching Circuits.
Wow. So Dennis grew up with this deep, tangible connection to that world of foundational research, the kind of long-term, deep thinking that Bell Labs was famous for.
Exactly.
Right.
He wasn't just walking into an office for a job. He was stepping into a family legacy, a tradition of deep scientific inquiry.
So after high school in New Jersey, he heads to Harvard. And his degrees are in physics and applied mathematics.
Which, when you think about it, is the perfect intellectual tool set for inventing a system language.
How so?
Well, physics gives you this rigorous understanding of, the underlying reality, the hard constraints of the universe. And applied math gives you the tools to model and solve real-world problems within those constraints.
It's the what is and the what to do with it.
That's a great way to put it. That mix is absolutely crucial for building software that needs to be efficient, elegant, and, mathematically sound.
But there's a fascinating academic footnote here that I think speaks volumes about the environment at Bell Labs versus, say, traditional academia.
Ah, yes. The famous missing PhD.
Right. So he completes a draft of his PhD thesis at Harvard in 1968. It's titled Computational Complexity and Program Structure. The work is done.
The work is absolutely done. His supervisor was Patrick C. Fisher. We have the records, but the source material is very clear. He never officially received the degree.
So wait, this is the genius who's about to rewrite the rules of computing, and he couldn't be bothered to file the final paperwork. What does that tell you about the priorities at Bell Labs in the late 60s?
It tells you everything you need to know. The work he was doing was so critical, so immediate, and so groundbreaking that chasing a formal academic credential just became secondary. He joined the Bell Labs Computing Science Research Center in 1967. By 68, he was already deep into projects that were moving way too fast for university timelines.
The innovation was just outpacing the bureaucracy.
Completely. The urgency of what they were building simply superseded the formality of getting the degree. We only know about this because in 2020, researchers found a copy of that lost dissertation. The ideas were proven, the formal title just wasn't necessary. His attention was already on a much bigger, much more practical problem.
And that problem brings us right into our first section, the context at Bell Labs and the genesis of Unix. And it's funny, we often talk about innovation, but sometimes failure is the best catalyst. And the catalyst for Unix was a massive, ambitious failure called Multics.
That is the perfect place to start the story. Multics, which stands for Multiplexed Information and Computing Service, was the dominant project that Ritchie and his colleague Ken Thompson were working on in the mid-60s.
This was the moonshot of operating systems at the time,
It
right?
was the Moonshot, a huge multi-user time-sharing utility designed for mainframes. It was a massive consortium project with Bell Labs, MIT, and General Electric. It was supposed to be the ultimate operating system.
So what went wrong? Too many cooks in the kitchen, too much ambition.
Precisely. Multics became a sprawling, overly complicated beast. It just demanded enormous resources, both in hardware and, frankly, in human effort. By the late 60s, Bell Labs realized the complexity and the cost were just way out of line with the returns.
It was too unwieldy for the tech they had at the time.
Exactly. So they made the tough, but as it turns out, incredibly transformative decision to pull out of the Multics project completely.
So Bell Labs is out, but Thompson and Ritchie are left with this intellectual itch. They still want to build a time-sharing system, but one that's simple, clean, and, actually works.
Yes, and this is where that famous anecdote comes in, the one about the old hardware. Ken Thompson, just determined to keep working on this, found an old, basically forgotten mini-computer kicking around the lab, a PDP-7.
And compared to the mainframes they were using for Multics, this thing was a toy.
An absolute toy. It had very limited processing power, tiny memory. But that constraint, that limited machine, it forced simplicity. It forced elegance.
There was no room for complexity.
None. Thompson decided to just start over. He'd develop a new operating system and new programs from scratch on this machine, and Ritchie and others quickly joined in to help. That shift from this huge bureaucratic project to a small, nimble team focused on one restrictive piece of hardware. That's the real origin story. They had to be smart, efficient, and just ruthless in their minimalism.
And of course, the name itself is pure Bell Labs humor, a pun on the very system they had just abandoned.
That's right. Multics, implies many, complexity. In 1970, another key figure, Brian Kernighan, suggested the name Unix, which was a bit of a self-deprecating pun. It implied the system was the opposite of Multics. Simpler, streamlined, focused on one thing at a time.
The power of that collaboration, Ritchie and Thompson, it just can't be overstated. Doug McElroy, who was also there, summed it up perfectly. He wrote that the names of Ritchie and Thompson may safely be assumed to be attached to almost everything not otherwise attributed.
They were the core architects, absolutely. Thompson built that initial OS structure, but Ritchie was already tackling the huge fundamental problem that could have killed the whole project.
The language.
The language problem. Thompson was initially working in assembly language, which is incredibly cumbersome and tied to one specific machine. To make Unix what it needed to be, flexible and portable, it couldn't just live in assembly.
Which brings us naturally to the precursor language.
Yeah.
B. This was Thompson's first attempt to move beyond the brutal inefficiency of assembly.
Right. Assembly language is basically talking directly to the hardware. It's fast, but it's a nightmare to write for large systems. And if you get a new computer, you have to rewrite everything.
So Thompson needed a higher level language.
A slightly higher level language, yeah. He created B, which was based on an earlier language called BCPL. It was meant to give them some structure, some speed in development, while still being low-level enough for an operating system.
So B solved the how fast can we write code problem, but it created new structural problems as Unix grew. Why wasn't B good enough?
This is a really crucial technical point for understanding why C was so necessary. B was extremely minimalist, which was great for that tiny PDP-7 machine, but it had serious limitations when Unix started to grow and they got a more powerful machine, the PDP-11.
What were those limitations?
Two big ones. First, B was typeless. Everything was just treated as a machine word, a chunk of bits. This made handling complex data, and especially defining the internal data structures of the OS, like file information or memory tables, really clumsy.
So it was hard to keep the system's data organized.
Exactly. But the second and maybe bigger problem was that B couldn't handle a key feature of the new PDP-11 byte addressing.
And what's that?
The PDP-11 could address individual bytes of memory, not just whole words.
Oh.
This is absolutely essential for working efficiently with things like characters and text strings. B was just incapable of using this fundamental feature of the hardware.
So B was a dead end.
Ritchie recognized it immediately. If Unix was going to evolve and be ported to new machines, B wasn't going to cut it. He needed a new language, one that kept B's elegance, but added the necessary structures and the ability to talk directly and efficiently to the hardware. That need right there was what gave birth to C.
So Thompson starts the OS, but it's Ritchie who builds the architectural tool, the language, that guarantees its survival and its future. That transition completely changed the destiny of Unix.
It really did.
And that's where we get into Ritchie's masterpiece. C is, I think you could argue, his single greatest invention. And its genius lies in what we call its dual nature. We have to really break this down because it's a paradox. It functions as both a low-level language and a high-level language at the same time. How does that even work?
This is the core reason C just dominated computing for decades. Most languages, they have to pick a side. You have your high-level languages like Python or Java today, which are fantastic for abstracting away complex logic. They're great for business applications.
But they're slow, right? They have a lot of overhead.
They often need a big virtual machine or an interpreter to translate their commands into machine code. That adds overhead, and it removes your direct control over the hardware.
And on the other end of the spectrum, you have assembly language. Super efficient, but basically unmanageable for a big project.
Exactly. C is the perfect hybrid. On the low-level side, C has constructs that translate very, very closely to the hardware's own instruction set. The big one is pointers.
Pointers give you direct control over memory.
Direct surgical control. You can allocate memory. You can manipulate it directly. This is essential if you're writing a kernel or device driver or firmware for a tiny chip. You get the raw speed and access you need.
So you get that raw machine-level speed, but then you layer on the structural clarity of a high-level language.
Precisely. Ritchie took the core ideas of B, but he added these crucial high-level elements. The most important were data types, so you can define integers, characters, and so on, and critically user-defined data structures. These are called structs in C.
And structs let you organize complex information.
They let you map real-world things like a user profile, a network packet, a financial record into an organized block of memory. That ability to organize and map complex data is the absolute hallmark of modern software development.
So C gives you the speed of a low-level language, but the organization of a high-level one. And for Unix, this duality meant one thing above all else: portability.
That word, portability, is everything. It's the whole ballgame. Before C, if you wanted to run your operating system on a new machine, say moving from that PDP-7 to a PDP-11, you had to rewrite most of it.
A huge undertaking. It basically locked you into one hardware vendor.
It was a massive commercial barrier. C completely shattered that. Because C abstracts the code away from the specific hardware, you could write Unix in C, and then all you needed was a C compiler for the new machine.
And you could just move the entire OS over.
You could port 90% of it with minimal effort. This ability to move Unix and all its applications easily across different processor families, from mainframes down to the first microprocessors, that is what made Unix a global force and C the master key to hardware independence.
That's a massive intellectual leap. It really defined how we think about software development from that point on. But even a brilliant invention needs a standard to really take hold globally. And that brings us to the famous book he wrote with Brian Kernighan, known simply by their initials.
The C programming language, published in 1978, famously known to every programmer as K&amp. And this wasn't just a book. For decades, it was the constitution of the C language.
Why was K&R so important? What made it so influential?
Well, a couple things. First, the language was still evolving, and K&R provided a definitive, elegant standard. It defined what became known as K&R-C, which was the de facto benchmark for years.
So it got everyone on the same page.
Exactly. And second, the style of the book perfectly mirrored the style of the language itself. It was compact, efficient, and crystal clear. It wasn't a huge, verbose textbook. It was a reference manual and a tutorial all in one. It let programmers all over the world learn the standard quickly and know that their code would work everywhere. It basically professionalized the language.
So K&R gives it consistency, which, combined with C's portability, just leads to its absolute dominance. It cements its reputation as the architectural scaffolding of modern software. Let's really try to quantify that DNA claim. Where do we see C's legacy today?
That claim that C is the genetic material of the modern software world is, well, it's provably true. I mean, C itself is still highly visible. It's used everywhere in operating system kernels, embedded systems, firmware, for everything from your car to your smart fridge, supercomputing.
Anything that needs to be fast and close to the metal.
Anything that needs raw speed and direct hardware control is still often written in C, but the influence is so much deeper than just the code that is still C. It's the language that basically spawned every other major modern language.
It's the linguistic root.
It is. C laid the structural and the philosophical groundwork for almost everything that followed. When you look at the syntax, the curly braces, the control flow, the way you define functions, that's carried forward into the derivatives that dominate the commercial world today.
You're talking about things like C++C.
Direct descendants, yes. C++A, which added object-oriented programming on top of C's core, Objective-C, which was famously used by Apple for years, and C#, which is the foundational language for Microsoft's entire .NET framework.
So the biggest players in tech built their empires on languages derived directly from C.
They did. And even languages that look pretty different on the surface, like Java and Python, owe a massive debt. Java's syntax is directly derived from C and C++. It's used everywhere in big corporate environments, and it's the foundation of the Android operating system.
And Python.
The core interpreter for Python, the engine that actually runs the code, is itself written in C for performance. So even when you're using a modern, high-level abstract language, the high-performance engine running under the hood is almost certainly C code, built on the design principles that Ritchie laid out.
Wow. So without C's ability to bridge that gap between efficient hardware access and high-level structure, the modern software ecosystem it wouldn't exist as we know it. It was the essential pivot point.
It really was.
So C may be Ritchie's defining technical achievement, but it was a tool that he forged for a very specific purpose, to enable Unix. Let's talk about Unix as a foundational system, because this is where that portability innovation really paid off.
This was the strategic masterstroke. The decision around 1973 to rewrite almost the entire Unix kernel in C. Before that, operating systems were written in assembly. They were proprietary, they were bound to the hardware they were sold with.
But by writing Unix in C, Ritchie and Thompson guaranteed its flexibility.
And its ability to be ported across different processors, easily, efficiently, and quickly.
Thompson got the ball rolling, but it sounds like Ritchie was the one who made sure it wasn't chained to one machine.
Ritchie was crucial in those porting efforts. He took on the really detailed, difficult work of moving Unix to different platforms. And this work didn't just validate C as a language, it demonstrated a whole new economic model for software. Companies no longer had to rebuild their entire system if they bought new hardware.
They just needed a C compiler.
They just needed a C compiler for the new machine, and they could bring Unix with them. For IT departments in the 70s and 80s, this was absolutely revolutionary.
But Unix was influential beyond just the code, right? It established entirely new ways of thinking about computing, principles that are now just baked into everything.
Oh, absolutely. We can point to several huge conceptual ideas that came out of Unix. First, the hierarchical file system, the idea of directories and subdirectories. Before Unix, data organization was often flat and just chaotic. This gave it a logical, manageable structure.
And then there's the philosophy of small tools.
Right, the idea that instead of building one massive program that tries to do everything, you build lots of small, specialized, reliable programs, utilities, that each do one thing and do it well.
And you chain them together.
You chain them together using the invention of pipes. The pipe mechanism lets you redirect the output of one program to be the input of another right from the command line. This ability to just combine small, efficient programs on the fly was immensely powerful. It's the foundation of all modern scripting and automation.
And finally, you have the model for processes and users.
Yes. Unix defined a really robust model for managing multiple users, concurrent processes, memory protection, the very structure of a modern time-sharing operating system. These weren't just implementation details, they were philosophical principles of modularity, simplicity, and composability. And they became the gold standard for every OS that followed, whether it was Windows NT, macOS, or Linux.
Ritchie was also key in documenting all of this, right? Spreading the philosophy.
Documentation was vital, especially for getting Unix adopted in academia. He co-authored the Unix Programmer's Manual way back in 1971. Later, the foundational academic paper, the UNIX Time-Sharing System, which he wrote with Thompson, helped formalize the whole model for computer science everywhere. These documents didn't just explain the code, they institutionalized the philosophy.
So let's bring that legacy into the modern era. The word Unix today refers to this huge family of derivatives. And Ritchie himself actually commented on this in a 1999 interview.
Right, and his perspective is so important because it validates the whole open source movement that came later. He consistently said that systems like Linux and the various BSD variants weren't just clones. He saw them as a vital, robust continuation of the fundamental basis of Unix.
The idea was bigger than the original code.
The idea was bigger than the code. And his comments on Linux are particularly telling because that was the phenomenon that really changed enterprise computing.
What did he say about it?
He was incredibly supportive. He said, and I'm quoting here, The Linux phenomenon is quite delightful because it draws so strongly on the basis that Unix provided. He called Linux among the healthiest of the direct Unix derivatives. He really understood the power of the open source model to advance the core ideas he and Thompson had pioneered.
Which reflects this core belief that it was about the evolution of the ideas, not who owned the code.
Exactly. He saw Unix and Linux as, in his words, the continuation of ideas that were started by Ken and me and many others many years ago. It was never about proprietary control for him.
And if you look at mission-critical computing today, I mean, that legacy is just undeniable.
Completely. The principles of Unix stability, security, scalability, they're still the standard. While Windows might dominate the consumer desktop, the source material is clear that the commercial derivatives, things like IBM's AIX, HPUX, Solaris, they are the de facto OS for anything that is mission critical.
They're running the world's infrastructure.
They're running global stock exchanges, massive corporate databases, telecommunications networks, supercomputing clusters. You simply cannot build a modern data center without relying on the architectural principles that Ritchie and Thompson laid down 50 years ago. That reliance speaks volumes.
Now, it's easy to just focus on C and Unix, but Ritchie was innovating at Bell Labs for his whole career. After those huge successes, he kept pushing, trying to move beyond Unix's own limitations. What came next?
Right. Well into the 80s and 90s, he was a central figure in two major successor projects at Bell Labs, Plan 9, and later the Inferno operating system. And these weren't just, Unix 2.0, they were radical attempts to reinvent the whole OS model for the age of networking.
So what was the big conceptual shift from Unix?
Well, Unix was fundamentally built for a single machine that hosted multiple users. Plan 9 and Inferno tried to make the entire network function as a single, cohesive computer. They extended the Unix philosophy of everything as a file to include network resources.
What does that mean in practice?
It means that in Plan 9, for example, accessing a remote server CPU or a printer down the hall or a file on another continent, it was all treated as if you were just reading or writing to a local file in your own file system. It was this beautiful, unified model.
So if Unix defined local time sharing, Plan 9 and Inferno were trying to define true, transparent, networked computing.
Precisely. Now, they never achieved the same widespread adoption as Unix. Commercially, they were probably too far ahead of their time, but they were intellectually groundbreaking and hugely influential in academic circles. A lot of their concepts later found their way into modern distributed systems.
And he was involved in the programming languages for those too.
Yes, he contributed to the language Limbo, which was part of Inferno. It just shows he was always searching for that next foundational architecture, even when the one he already built was completely dominant.
Okay, let's turn to a really fascinating, almost hidden chapter in his career. A piece of classified history that shows his depth in fields way beyond operating systems, specifically cryptography.
This part just adds so much texture to his profile. During the 1970s, Ritchie collaborated with two other researchers, James Reeds and Robert Morris, on a highly technical cryptographic attack.
And the target was the M209 US cipher machine. For anyone who isn't a history buff, what was that?
It was a mechanical, portable cipher machine, widely used during and after World War II. It used a series of adjustable rotors and a paper tape key to encrypt messages. It was very secure for its time, but, purely mechanical.
And the attack they developed was a ciphertext-only attack. That's the hardest kind, isn't it?
It is the holy grail of cryptanalysis. It means they only had access to the encrypted message, the scrambled text. They had no idea what the original message said, and from that alone, they could figure out the original message and, crucially, the machine settings used to encrypt it.
That requires some serious mathematical skill.
Immense computational skill, a deep understanding of statistics, probability theory, basically finding the subtle mathematical weaknesses in the machine's design, and their attack was devastatingly effective.
How effective?
The source material says their method could solve messages of at least 2,000 to 2,500 letters just from analyzing the ciphertext. This wasn't just an academic exercise, it was a practical demonstration of a major vulnerability in an established cipher system.
And yet, this research was never published. It stayed secret for decades. Why?
This is where Bell Labs research intersects with global security. After they did the work, they had discussions with the National Security Agency, the NSA. And the NSA pointed out that the principles they had exploited still applied to similar mechanical cipher machines that were still in active use by foreign governments around the world.
So they were sitting on a live, intelligence vulnerability. If they published it, they could compromise ongoing global communications.
Exactly. So, out of a sense of responsibility for national and really global stability, the authors just collectively decided not to publish it. They suppressed their own research. It's a remarkable insight into the high stakes ethical environment at Bell Labs. It shows Ritchie wasn't just a genius coder, he was a responsible scientist who understood the real world implications of his work.
Moving from secrets to recognition, Dennis Ritchie's work, while often invisible to the average person, was recognized for decades by the highest institutions in science and tech. And it really started with the computing world's ultimate honor.
The pinnacle, yeah. In 1983, he and Ken Thompson jointly received the ACM Turing Award. It's often called the Nobel Prize of Computing. And the citation was very specific. It was for their development of generic operating systems theory and specifically for the implementation of the Unix operating system.
That phrasing is so important. They weren't just awarded for building a thing, they were honored for advancing the theory of how operating systems should even work.
That's the key. Ritchie's acceptance lecture was titled Reflections on Software Research, and it's this profound look at the thinking behind C and Unix, the need for simplicity, the power of modularity, the importance of bridging hardware and human logic. It set the standard for what system theory should be.
And that pattern of joint recognition for the two creations, the OS and the language, just continued through the 90s.
It did. 7 years later, in 1990, the IEEE gave them the Richard W. Hamming Medal. And again, the citation focused on both halves of his contribution for the origination of the Unix operating system and the C programming language. It's just so rare for one person to have that level of influence on both the architecture and the tool used to build it.
And their status as foundational figures was cemented by the Computer History Museum.
In 1997, yeah. They were inducted as Computer History Museum Fellows. Again, for co-creation of the Unix operating system and for development of the C programming language. This trio of major technical awards really placed them in the pantheon.
But the biggest, most high-profile honor came from the U.S. government, recognizing not just the academic achievement, but the massive global impact.
That would be the National Medal of Technology. Thompson and Ritchie received the 1998 award, and it was presented by President Bill Clinton in 1999. And the citation for that medal just spelled out the immense scope of their influence far beyond the lab.
What did the government citation say? How did they frame the impact?
It was incredibly clear. It said their work led to enormous advances in computer hardware, software, and networking systems and stimulated growth of an entire industry, thereby enhancing American leadership in the information age.
Wow. So that's a direct line from their lab work to global economic stimulus and American technological leadership?
There's no ambiguity there. Few pieces of software have ever received that kind of sweeping recognition for their societal and commercial impact.
And he kept getting honors well into the 2000s.
He did. In 2005, the Industrial Research Institute Achievement Award. And finally, in 2011, right before he passed away, he and Thompson were awarded the Japan Prize for Information and Communications. This 3-decade string of honors just confirms that his work wasn't some transient innovation. It's a permanent, growing foundation for the modern world.
So, after this incredible career, how did his long tenure at Bell Labs and its successor companies finally wrap up?
His career was almost entirely within that one research ecosystem. During an AT&T restructuring in the mid-90s, his research center was transferred over to Lucent Technologies. He continued his work there, eventually moving into a leadership role. He retired in 2007 as the head of the Systems Software Research Department at Lucent. Just a long, distinguished career spent quietly building the world's infrastructure, largely shielded from all the commercial noise that his inventions had created.
And the final chapter of his life, unfortunately, really illustrates his role as the unseen architect. He was found dead on or about October 12, 2011. He was 70 years old, living at his home in New Jersey. He'd been in frail health for a few years after treatment for prostate cancer and heart disease.
And the timing of his death is just so critical to understanding his public profile. The news of Ritchie's death was almost completely overshadowed by the intense global media coverage of the passing of Apple co-founder Steve Jobs, which had happened just the week before.
Which created this stark, almost poetic contrast.
Yeah.
You had the high-profile, consumer-facing icon whose products defined user experience.
Versus the foundational internal architect whose work made all of those products even possible. The media really struggled to explain Ritchie's influence to the general public.
And that contrast became the key to summarizing his legacy. The computer historian Paul Ceruzzi captured it perfectly. He said Ritchie was completely under the radar to the public. But then he offered this powerful analogy.
If you had a microscope and could look in a computer, you'd see his work everywhere inside. He was the quiet, fundamental structural pillar. That's the perfect image.
Even those closest to him, like Brian Kearney and his co-author, said that Ritchie himself never expected C to become so significant. He just built it as an elegant tool for system programming, not as a universal language.
And Kernighan was the one who provided that clear bridge for everyone, connecting Ritchie's unseen work to the consumer world. He said, the tools that Dennis built and their direct descendants run pretty much everything today. And he specifically pointed out the essential role of C and Unix principles in the code that underpins the iPhone.
The link is just undeniable. When commentators look back at the relative importance of Ritchie versus Jobs, the consensus was clear. Ritchie's work played a key role in spawning the technological revolution of the last 40 years, including technology on which Apple went on to build its fortune.
Which brings us back to that idea of the foundational scaffolding. One commentator put it perfectly. Ritchie invented and co-invented two key software technologies which make up the architectural underpinning of effectively every single computer software product we use. And that's not hype. It's just a statement of technical fact.
The computer science community certainly understood the loss. We saw some really moving tributes from the open source world, the same movement that Ritchie had praised so strongly.
Oh, they knew. They knew where their freedom and flexibility came from. Two major operating systems dedicated releases to his memory, the Fedora 16 Linux distribution and FreeBSD 9.0. It was this acknowledgement of the deep philosophical debt they owed him.
And there's one lasting tribute that really places his legacy among the great thinkers. His name is now literally in the stars.
It is. Asteroid 294727, Dennis Ritchie, discovered in 2008, was officially named in his honor in 2012. The quiet architect whose work underpins the systems we use to explore the universe now has his own place within it. It's a beautiful, fitting end to a life defined by foundational work.
So as we wrap up, what stands out to you as the ultimate takeaway from this deep dive into Dennis Ritchie's unseen empire?
For me, it's the recognition that the truly revolutionary changes in technology are often structural and they're often invisible. Ritchie was the quiet genius. He was the indispensable architect who, with Thompson, birthed Unix and then single-handedly engineered C, that critical bridge that lets software be portable and efficient and just fueled the global explosion of software development.
His inventions are the absolute bedrock of modern operating systems, running everything from proprietary workstations to the Linux kernel and the fundamental code inside virtually every smartphone. He retired from Lucent in 2007, leaving this legacy that was acknowledged by the highest honors. From the Turing Award to the National Medal of Technology, he abled the information age by building its tools.
Right. Now, we talked a lot about how his work on Unix established these core computing concepts, the file system, process management, and so on. We also know he spent his later career trying to move past Unix's limitations with systems like Plan 9 and Inferno, which proposed radical new models for networking.
Which raises an important final question for you, the listener, to think about as you use technology today.
If C and Unix defined the last 50 years of computing by establishing principles like the hierarchical file system, what foundational concept, hidden deep inside our modern systems and derived directly from 1970s Unix, are we still relying on today that is now becoming a constraint? What specific structural part of the Unix philosophy needs to be replaced or re-engineered? Maybe it's about security or distributed identity or data flow to enable the next truly revolutionary shift in computing.
We rely on these structures every day. But are they secretly the ceiling for the next great innovation? A profound thought on the architecture we all take for granted. We hope this deep dive encourages you to look a little closer at the code that runs your world. Thank you for joining us on the deep dive.